some comments on problems that that have been submitted. There's a case where we have a mass M1 on an incline, a mass M2 hanging from a pulley over the edge of the incline, so that the force on the system consisting of masses M1 and M2, so the system consists of this connected pair of masses, and the cord, which has no effective mass, no negligible mass. What do we have? We have gravity acting down on M2, we have gravity acting down on M1. However, there's also a normal force. I haven't indicated it, but there's a normal force between here and the incline. And if there's no other force acting other than gravity and the normal force is equal and opposite to the component of the weight, M1G, perpendicular to the incline. The component parallel to the incline, of course, directly affects the acceleration. The component perpendicular to the incline has no direct effect on the acceleration. But of course, if there's friction, then the component normal to the incline, balanced by the normal force, results in a friction force. So what is our situation here? I see people doing all kinds of intuitive things, but I don't see a really good, coherent way of setting this up. So I'm seeing a lot of good, correct solutions, even though they're not structured the way I'd like to see them. But I'm seeing some errors in the solutions because some things are missing or because things aren't quite exactly sorted out. Okay, so what do? We always look at the net force. What's the net force acting on this system of two masses? Well, you have the force of friction, which acts between this mass and the incline. You have the x component of the force of gravity. That would be the M1Gx, if you prefer. And then you have the M2G that's acting here. Now, all the acceleration can be considered to be in one dimension, so I haven't put arrows over these, but rather than arrows, we're going to use plus and minus signs for these forces. Or you could use arrows if you want to. It's going to just still result in plus and minus signs. Now, we have information, sufficient information, to determine the acceleration of this system. I think it was 2.7 meters per second squared. That wasn't given, but you were given that it goes from rest to a certain distance at a certain time. And then you easily enough find the acceleration. And if you multiply the acceleration by the mass of the system, you get another expression for the net force. So you set this expression for the net force equal to this expression for the net force. We see that M2 is the unknown quantity in this case. We were given the mass M1, so we have to find M2. But we see now that once we get the expressions for these forces, we're going to have M2 here, we're going to have M2 here, and we're going to be able to put it all together and solve for M2. Okay? Now, another situation here. We have two masses now on two inclines. Rather than one mass hanging directly off of one incline, we have two masses on two inclines. And I think in this case, we were able to assume that the frictional force is zero, but if there is friction, that's easy enough to determine. Well, we want to find the net force on this system. And of course, that's going to be, there's going to be a weight here, and you're going to have the component of the weight along this incline, and then there's a weight here, and the component of the weight along this incline, calculated in the usual manner. And you get a net force. You know the two masses, so you get the total mass, and you divide the net force by the total mass to get the acceleration. That much is straightforward. Now we want to get, what I want to address is finding the tension. To find the tension, this is where people tended to make some errors. Not everybody made errors, but several people did. Most people got the net force and the acceleration by resolving forces and did that just fine, even though I would rather have seen it done with a 360-degree coordinate system. Rather than a canned formula that it's easy to get wrong. But anyhow, if we isolate either mass, and we're going to isolate one, we choose this one. So here's the isolated mass. And here's your mg for this mass in the x direction, assuming we have the x direction this way along the incline. And then we have the tension opposing that. And the tension is what we don't know. We can find mgx. We already found that in the process of finding the net force over here. So all we have to do is find the tension. Well, what do we have? We have tension, we have mgx. You put these together, you find that the net force is tension minus mgx. You already have found the acceleration, and you know this mass, so you can set this equal to the mass times acceleration and solve for the tension. And it becomes very easy. Rather than some intuitive idea, which people used and for the most part I think got right, you have an airtight expression for net force here, and you have an airtight expression for net force here. So, and what a lot of people did was they just added the acceleration to the acceleration of gravity to find that tension, or to find something that they regarded as some kind of a net acceleration. You don't really have that great of a simple interpretation of what you would get if you add this acceleration to the gravitational, or at least to the x component of the gravitational acceleration. Okay, anyhow, this bottom line is I want to see net force. I want to see two expressions for the net force. That's for your own good. So try to get in the habit of doing that. There was another case where we had, we had a weight sitting on top of another weight, and an incline and a wall here with an attachment, a cord attaching the top weight to the wall. And how do the forces come out of this? Now, I haven't drawn a free body diagram. I've just illustrated the forces on a big old diagram here. This weight, I think, is 3 times this weight, so we have 3 times the weight 1 acting down here. We have weight 1 acting down here. We have F1 normal, which is the normal force on what I call weight 1. This will be the first object. This will be the second object. Okay? So we also have F2 normal, the normal force between the second weight and the incline, and that's going to be bigger. And then we have the coefficient of friction times F1 normal. That's the frictional force between this mass and this mass. And then we have coefficient of friction times F2 normal. And this F2 normal is pretty obviously bigger than F1 normal, but you want to work that out. So we have another frictional force. So when we try to get the net force on this mass, what are we going to have? We're going to have the x component of this weight, okay, about this, and we're going to have this frictional force and this frictional force pulling back. So not everybody got all the details of that picture, so I wanted to clarify that so you can go back and take a better look.